in the last class, we started talking about a new topic, which is this idea of surface flows. And here, the basic idea is that there are many situations when you are dealing with granular materials in which you have flow of particles on a fixed bed of the same material. So here are some examples like flow on a heap, flow on a fixed bed. So there's flow and then there's a fixed bed of flow in a rotating cylinder where you have a flowing layer and a rotating fixed bed. And though the flow properties are as before, but the additional feature here is that some particles may deposit on the surface, or because of the flow the surface can actually get eroded. That means particles can come out from the fixed bed and go into the flowing layer. And of course, if there's, like in this case, when there's steady flow, then the interface just becomes a fixed interface and doesn't change with time. But in many cases, this interface may change with time, and so we have to understand what is the rate at which things deposit and what is the rate at which they are eroded away. And what I told you is that there are, supposing you have, this is the flowing layer and this is the fixed bed, and let's say that makes an angle theta to that. Then there have been a couple of models which are just phenomenological models. That is, they are not based on some theory or something, but they're based on physical expectations. They said that okay, these here gamma is the rate at which particles are deposited, and this gamma has the units of velocity, and so gamma is this rate of deposition. And what it says, if you look at this equation, then if theta is greater than theta n, then this quantity is negative, and so you have erosion. So instead of deposition, since it's a negative value, so it is being eroded, particles will keep on getting removed from the bed until the angle becomes equal to theta n. So the angle changes as the erosion occurs. However, if theta is larger than the neutral angle, that means you have a much steeper slope. I'm sorry, if theta is less than theta n, that means the angle is less, maybe angle is 0, then particles will keep on depositing on it and the angle will keep increasing until you hit theta n, where this theta n is just the neutral angle. And at steady state, when there is no deposition or no erosion, then this angle will be equal to the neutral angle. So this is really the model, and depending on the angle, you will get different kinds of dynamics. Either there will be erosion, that is particles are removed from the bed, or deposition, where particles are put in the bed. So we want to really look at these types of problems and see how we can come up with equations to describe the flow in the layer and the rate of deposition and so forth. And to do that, last time we started talking about this idea that supposing we have a thin flowing layer, that is, this thickness is much smaller than the length L, then you can just neglect the curvature of this, and we can pretend that this is just actually a straight interface. And then for simplicity, we can also assume that that we can assume this velocity profile is linear. So it's the shear rate times the distance y from the interface. So you have a linear velocity profile. This is a good approximation. again based on experimental studies, many of the places you have actually a linear profile when you have this kind of flow. Again, delta is the thickness of the layer, u is the mean velocity in the layer, and it's essentially equal to the integral of dx from 0 to delta. That gives you u. And supposing this flow is occurring between two vertical walls, so then in the z, along those walls there will be wall friction, which is given by mu w into sigma zz. Now, what I want to do is basically I want to describe this flow, but using a depth averaged equation. That I want to average every term in the equation from 0 to delta. So I'm not worried about how things vary within the layer, but I'm interested in how the thickness changes, how the mean velocity changes, how this angle changes as we go, and what is the rate of deposition. So I would like to start with the mass and momentum balance equations, average them like this, and then just understand what is the physics of this type of flow. And then once we have those equations, then we can look at very many specific examples and actually get a solution for those. So in this lecture, what I'm going to do is I'm going to try and derive these depth average equations, and then we'll do some examples of this. Okay. So go to the go back to what we were doing in the previous class. So this is what we had started doing, depth average equations for surface flow. So then let me just start again. So what we want to do is we want to today's lecture 29 and the date is 11/10/21. Okay, so really we want to continue doing what we were doing last time, and that is the depth averaged equations. By depth averaged, as I mentioned earlier, this is averaging over y from. So here is our system again. Here's my interface. This is the fixed bed over here. This is my flowing layer with a linear velocity profile. And here this distance perpendicular to the layer is called y. The distance along the layer is called x. And the thickness of this layer is delta. And of course, the angle made by the interface, this angle is beta. Okay, so what we've already assumed is that rho b is a constant. Vx is just equal to gamma dot y, which is nothing but 2 times the mean velocity by delta into y. Gamma dot is just this, the maximum velocity by delta. So these two things we've assumed, and then let's suppose in the z direction there are walls, And there also we have said that wall friction is given by sigma xz is equal to mu w into sigma zz. So this is the normal stress on the wall. Mu w is the wall friction. So these things we've assumed. We'll have many more assumptions as we go along. But let us go systematically. Here this should have a minus sign. Okay. So I want to start, and we have decided to look at the momentum balance equation. So now let me go a little one step further back from what I was talking last time. We know that the momentum balance equation is given by okay. So this is in terms of the total stress. And what I said is that we can actually write this V dot gradient of V. And I think you might have done this before. This is just equal to divergence of rho B into V plus V into divergence of so this is what you would get. Okay. And a continuity equation can also be written as del rho B by del T dt is equal plus divergence of rho B into V is equal to 0. So this is the momentum balance and this is the continuity equation. So these are the two equations that we'll use, but I want to transform this momentum balance equation into something slightly different. And so if I write this as del of del T of rho B times V plus divergence of this is minus here rho B into V, then this is nothing but rho B del V by del T plus V del rho B by del T. And then this one, if I expand the second term, if this term, if I expand, again, these all you can prove, then I will get del rho B V dot gradient of V plus V into divergence of rho B times V. So this is what you will get. And so now if we use the continuity equation, then you can see that these two terms will go to 0. So this I'll write is just equal to rho b plus v into del rho b by del t plus divergence of rho b times v. So you see this? So this term from the continuity equation, you can see that this term is just equal to 0 from the continuity equation. So now what it proves is that del by del t of rho b v plus divergence of rho b v v is just equal to rho b into del v by del t plus v dot gradient of v. So this is what we get. So this allows us to put this momentum balance equation in this form. And so now if we substitute for the right hand side, we have already seen that rho b del v by del t plus v dot gradient of v is just equal to this. So then I can write down divergence of sigma, where sigma is the stress, plus rho b into g. So this is another way of writing the momentum balance equation. And so this is what we'll use. So we have this, we will use as a continuity equation. Okay. And then this we will use as a momentum balance equation, which is del by del t over rho b into v Okay, so these are the two equations that we will use, and we are going to integrate both of these equations from 0 to delta. So now if we let's look at the x component of this equation. So if we look at the x component for rho b to be a constant, then density can easily be pulled out, and then you'll have rho b del Vx by del t plus del by del x of Vx plus del by del y of Vx Vy. So this is the right left hand side, and this is equal to del of sigma xx by del x plus del of sigma xy del y del sigma xz of del z, and then of course plus the density, I mean the gravity term, it's rho bg into sine of beta, where beta is the angle of the interface. So this is what the equation reduces to, and this is where I was starting from last time. So what we'd like to do is now, just first thing is just average in the z direction, just to go back to this figure. So this is X, Y, and Z is perpendicular to the screen. So, we imagine there may be two walls or something that might apply some friction. So we just average over the Z. And if you average over the Z, then, all the terms will essentially become the mean values. So I'm just going to put an over bar to signify that this is the mean value. So what we'll do is we'll average. That means if there's any quantity alpha and alpha bar, this just means 1 by B, where B is the width, and that is going to be from 0 to B of alpha dz. So this is what is defined as the average. And if we do this average, then what you will get is rho B So all of these are just integrated and divided by B. And the only term that is not an average, because here we can easily just integrate it out. So this will just give us 1 by B into sigma xz evaluated between 0 and B, because this term can be integrated. And then of course you have plus rho bg sine of beta. Since this is a constant term, when you average it, it remains the same. And now, at 0, tau xz is 0, and at B it's equal to minus mu w sigma zz. So if we put that in, then we will get the result, that is that instead of here, I'm going to just write down the right hand side. So this is just equal to del sigma xx bar by del x plus del sigma xy bar by del y plus, and this now just becomes minus both. Replace this by so it becomes minus. Actually, B is at both points, the thing is the same. So this is actually minus 2 mu w sigma zz divided by B. And the sigma zz is evaluated at B. But we just leave this as it is. Okay. Now, what we need to do, the next step is integrate with respect to y. This whole equation, we'll integrate this with respect to y, going from 0 to delta. So if we do this, you'll get rho b del by del t. Take this out. Integral from 0 to delta of vx bar dy. Okay. And then the second term will be del by del x, and then integral of vx squared dy from 0 to delta. And now the third term will be just, you can do that integral. So it's just Vx, Vy bar evaluated between 0 and delta. And this is equal to, now here del by del x, so it's of integral from 0 to delta of sigma xx bar dy. Here plus del, now here this one just goes, you just integrate it. So this is just sigma xy bar evaluated between 0 and delta, because you can do the integral since we are integrating with respect to y. And then you have minus 2 mu w by b of integral of sigma zz dy from 0 to delta. And then the last term is a constant. So it just, when you integrate it with respect to y, going from 0 to delta, you just get rho bg delta sine of beta. So this is your momentum balance equation after integrating with respect to z, which is across the channel, and then with respect to y, which is across the depth. So this is the depth averaging we are talking about. So we'll make one more simplification. So this is one assumption further. Let's suppose that the normal stresses are all equal, and we say that sigma xx is equal to sigma yy is equal to sigma zz, and this is just equal to the pressure, which is rho bg into delta minus y cos of beta. So this is like how we did for the flowing layer. That's why I'm not bothering about doing the analysis. We already found out that the pressure increases linearly at the free surface at y equal to delta x 0, and then it increases linearly like this. So this is just like the pressure. So once we assume something like this, then we can easily substitute back in there, and what we get for each of these terms, we can get something. Now sigma xx integrated over dy from 0 to delta, and for sigma xx integrated over 0 to delta. So what you will get is, both of these integrals are exactly the same since they are equal. And both of these are just equal to rho b. That is, if you integrate this with respect to y and go from 0 to delta, what you will get is rho bg delta squared by 2 into cos of beta. So for both these we have something. And one more thing that we can do is that, tau xy at delta is just going to be equal to 0. That's at the free surface. You always have, so that equation also simplifies a bit. And then you can also do some further integrals. You know already that Vx, integral of Vx, we know what is Vx. So we also know that integral of Vx bar dy from 0 to delta. This is just equal to integral of gamma dot y dy from 0 to delta, and so there is just gamma dot delta squared by 2. So that is what is Vx average. And if you want to write it in terms of u, then we know that gamma dot is just equal to 2u by delta. So then, you just get Vx average. This is just equal to u times delta. Similarly, we can do for the next term where we have Vx squared. So this we can again write 0 to delta of gamma dot squared y squared dy, which is equal to gamma dot squared delta cubed by 3. And again, if we substitute for gamma dot is equal to 2u, so then this just becomes 4 into u squared delta squared by 3. Okay. Is this okay? I'm making some mistake. Yeah, sorry. This has to be, since I'm dividing by delta squared, this is just u squared into delta divided by 3. Okay. So this is all correct. Now all of this we can put back in this equation. Also we need Vx, Vy. So if we look at Vx, Vy average integral between evaluated between 0 and delta. Now at y equal to delta, if we go back to this, so you see at y equal to delta, at y equal to delta, the velocity will be Vy will be equal to 0, and at y equal to 0, you see here Vx is equal to 0. So since this is so the product is always 0 at both the limits. So this term simply goes off to 0. So now we can put everything, we know every term in here, and so we can now simplify this, and so what you will get is rho b del by del t. Now the first term you can see from here, we've already found out this is nothing but u delta. The second term is, now we see it's for Vx squared, this term. So Vx squared d by dx of Vx squared, and that is nothing but 4 u squared delta by 3. Then the third term, that is Vx Vy, this term is 0. Then we have del by del x. And here we substitute for sigma xx, which is just rho bg delta squared by 2 cos of beta, and then we have the next term is the shear stress. So we've already seen that this is just minus sigma xy at 0. This is something we still need to know. And then our third term is just minus 2 mu w into minus 2 mu w by b into this integral of the normal stress, which we have already found out is this, which is rho bg delta squared by 2 cos beta. So this is the frictional term. And then finally, of course, we have the term due to gravity. So this is what we get. So now the only thing that is missing is we need one expression for this. So let's suppose that again, this is an assumption. We don't know what is sigma xy, but suppose sigma xy at 0 is equal to some constant c, which is not known, rho b into d into delta minus y times gamma dot squared. So supposing this is what it is, plus, so this is sort of a collisional term, plus rho bg cos beta into some coefficient of friction times delta minus y. So we have a linearly increasing shear stress in this as expected, and one term is proportional to the velocity gradient squared, and so this is if you are supposing you are coming supposing you are coming from here, then the stress due to this velocity gradient and all is given by this. But supposing you were coming from here, that is from the fixed bed, and you come over here, so then you'll have another expression for the stress because there is no velocity gradient there. But then we must have a higher coefficient of friction. So we can also write it as, so this is for the flowing layer. And then we can also write the same thing for the fixed bed. In the fixed bed, it's just purely frictional. So you'll have rho Bg cos beta into another coefficient of friction mu m times delta minus y. So this is really the two things. And since the stresses are equal at the interface, I won't write this. This is not at 0. This is just generally the stress in the flowing layer, and this is the what we expect that this will be in the fixed bed. See, they're not evaluated at 0, but they are at any point. Now, if you say that at y equal to 0, both are equal, so I'm just going to call this by something that L will define the flowing layer and B is the fixed bed. But at the interface, both of these must be equal. So we must have sigma xy in the flowing layer equal to, so this is at 0, it must be equal to at the fixed bed again at y equal to 0. So if we do this, then we'll have C rho b d into delta gamma dot squared plus, so I put y equal to 0 here, is equal to rho bg cos theta mu m into delta. So, if you look at this, this gives us essentially an expression for gamma dot. And so you can see that delta cancels out everywhere. So you can see this delta just cancels out. And rho b also cancels out. So these two things cancel out. But then what you get is that gamma dot squared is just equal to g cos beta into mu m minus mu s divided by CD. And then you can take the square root of this. If I just do it a little, so you just get this. So you get, if we assume this to be the shear stress, then you can clearly see that this is the shear rate that you will get. And now, if we put this in to the equation, and so then the momentum balance equation then just becomes rho b into del by del t of u times delta plus 4 by 3 del by del x of u squared delta is equal to half. So this is the normal stress term. And then you are just left with the driving force minus all the resistance terms. So if you combine them all, then you get rho bg delta into sine beta. So this is the gravitational driving force. And then minus mu m cos beta. So this is essentially tau xy or sigma xy. So this is the internal friction term. I'm using essentially this equation in there at y equal to 0. So I'm using, that's why I get mu m. I could have just as easily, instead of this, I could have used this thing, but just for simplicity, I'm using this. And then we have one more term, which is the resistance due to friction. And that gives us mu w cos beta delta by b. So really what you see is this term, if you see, this term here is basically just the, and you can think of this as just the acceleration of the particles in the layer. This term comes because of changes in the uh, thickness, and this term is often referred to as earth pressure. So because the thickness is different in different places, there is a sort of higher pressure in some places and lower pressure in others, and so it affects the flow. And if you see this term, you can think of as the net driving force. So this term is usually always positive, and what it is gravity minus the frictional resistance of the bed at the base minus the frictional resistance due to the wall friction. So this is, you can say, the momentum balance equation. And for many situations, what you find is that this term, earth pressure, is almost equal to 0. So we can neglect that, because usually the changes in thickness are not so large to create a large earth pressure. So del D by del X is D delta by dx is usually quite small. So we can usually neglect that term. And so then we are left with a quite simple equation. And we can cancel out rho v from everywhere. And so, the momentum balance equation then simply becomes del by del t of u delta plus 4 by 3 del by del x of u squared delta is equal to g delta into sine of beta minus mu m cos beta minus mu w cos beta into delta by b. So this is really the simplified momentum balance equation. And this is nice because it takes all the physics into account. And so we have made a few assumptions, but essentially it takes the key ideas of momentum and so forth into account. Now I started with this, but let's do now. So this is nothing but the x momentum okay. So we have this equation. Of course, u and delta are unknowns here, and then there is one relation between u and delta, because we know gamma dot is 2u divided by delta. So that will give us one more sort of relationship. So we can actually solve some problems based on this. So we can eliminate u and just solve equations just based on these two things. But if you remember, the whole reason for doing this is we want to find out what is the rate of deposition and what is the rate of erosion. So actually we have a third variable, and if we go back to our previous lecture, then we see that really we would like to have this gamma also. What is the rate of deposition? So can we find it out from the theory? And it turns out yes, but you have to then solve the continuity equation. So with these two equations, If we call this equation as 1 and if this as 2, then together with these two equations we can easily get both u and delta, but we need the continuity equation to get the deposition rate and the erosion rate. So if we write down the continuity equation as we had done above, if we write this and then we do so when we do with respect to z, then there is no real difference. We'll get exactly the same thing back. And when you do with respect to y, then you'll get del by del t integral rho b dy from 0 to delta plus, okay, now this we must open out. Before I do the integral, let me just open this out and put it in scalar form so I can do the integral. So here you'll have del rho b by del t plus del by del x of rho b times vx plus okay, now you integrate with respect to y and z as above for the momentum balance. And if you do this, as I said, integral with respect to z makes no difference, but with respect to y, we'll get this. And then this term is just rho b into Vy from 0 to delta is equal to 0. So now when we do this, here, you get rho b out as a constant, and then you get del by del t of delta plus del by del x. Now this one we have already done before. So rho b is out, and this will be u times delta. And then here you have at Vy equal to, at y equal to delta, at y equal to delta, Vy is 0. So this is just plus, minus of rho b times Vy is equal to 0. Again, in this, the density cancels out everywhere. And so what we get is, we know that our gamma is the rate of deposition, so that is equal to minus of Vy at 0. Because it is depositing, so that is a velocity in the negative y direction, so that's why it's minus of Vy. So essentially, when we simplify this out, we'll get one more equation. So this is now equation number 3. So we have 3 equations, and then the unknowns are U, delta, and gamma. So we can essentially solve for them. Okay, and so we'll look at some examples. Of course, it's even more, a little bit more complicated because beta is also, you can think of as an unknown, so you need some more equations for that, and we'll see that. But for the time being, we can say that there are 3 unknowns and 3 equations, and we'll solve for those. Okay. Okay, so we'll stop.